Alright, so for vertical spring, it mentioned that, alright, the spring force equal to the gravitational force. Spring force is a Hooke's law. F equal to kx, right? So gravitational force is a Fg equal to mg. So by using the equation, summation of F means that the total F net, okay, equal to F minus with Fg. So why it's minus here? Because as you can see here, F is going upward, alright? So Fg is going downward. That's why this one is positive, this one is negative, because gravitational force is going downward. Alright, so 0 equal to kx minus kx naught. X naught here represent the equilibrium position of the spring. As you can see, okay, this is the equilibrium position x of the spring before the mesh are stretched, before we put a mesh attached to the spring, before the spring start to oscillate, minus with mg, right? So then, okay, so then, alright, sorry, so F net, total F here equal to, okay, F minus Fg equal to 0. So then we rearrange the equation, rearrange by putting the 0 in the right side and this one moves to the left side. That's why we got a F minus Fg equal to 0. So F is kx naught minus with mg equal to 0. So moving it to the right side. So we got the mg minus with kx naught equal to 0, which is, this is the equation that we got. Alright, so from here we can find the original or origin position of the x naught or equilibrium position of the x by using the equation mg divided by the k. Mg, mass of the object, time with gravity divided by the spring constant. Okay, so the second x naught here is equilibrium position. X here after the spring start to oscillate or when we attach the mass to the spring. So we now measure x, a new x from the equilibrium here. So if let's say x here we got a 5 and then the original position of x is 3. So means that x here, so we need to change, we need to minus with 3, 5 minus with 3. Then we got a x. That is the new value of x, which is a 2. That is the how to find the x. Right, so we need to minus with a equation of, we need to minus with the original position. This is example value only. I just now want you to understand more about the displacement. All right. This is a summary of the variable in simple harmonic motion. Displacement, the distance traveled by the mass, all right, measured from the equilibrium position. Mass minus with the equilibrium position, or must take the distance from the equilibrium position. So the unit is meter. That amplitude is the maximum the displacement, that the maximum the mass of the spring are moving. Alright, the unit is still a meter. So the difference is a maximum word here. Alright, a cycle, that a full to and fro motion means that from a maximum negative x to maximum positive x. That is we call as a cycle. For example, alright, this is our graph. Alright, the displacement versus time, for example. So this is our starting point. So means that from the starting here until it's complete one cycle. So that is a, we call as a cycle. Alright, period, the time taken for one complete cycle. So the period here is from here to here. Right, so this one is period. Alright, one complete cycle. Unit is second. Then frequency is the number of one complete cycle in 1 second. So means how to find the frequency by 1 over t. Okay, frequency, how many cycle, one complete of cycle in 1 second, as we have looked in the earlier slide. So unit is per second, okay, or hertz. So from there we can define a new, we can use the equation of omega, or angular frequency or angular velocity, equal to 2 pi f that we already learned in chapter 1. So from here we can find frequency with using this equation, omega divided by 2 pi. This one for one complete cycle. Alright. force law in simple harmonic motion. So by using the Newton's second law, alright, because an object that undergoes simple harmonic motion obeys Newton's second law of motion, which is from the equation F net equal to ma, or summation of F equal to ma. So we know that a equal to negative square x, as we have learned in chapter 1, how to find the a, okay, related to the omega. So x equal to a equal to negative omega x, or equal to a equal to r omega squared. We just change the variable r to x, and the negative here represent the differentiation of the acceleration. Alright, later we see how to get this equation. So we just remember what we have learned in chapter 1. So then we just substitute the equation here in the Newton's second law. Alright, replace a by negative omega square x. Then multiply, we got a new equation of F net for simple harmonic motion. Alright, which is F equal to negative m omega squared multiplied with displacement. So don't label this one as equation number 1. So since m omega squared is a constant, it can be deduced that, alright, it is a constant. How do you know this one is constant? Refer to the Hooke's law. Because of Hooke's law, F equal to negative kx. So new equation that we got from the Newton's second law related to the rotational motion or oscillation or motion in simple harmonic motion, we got a negative m omega squared x. As you can see here, this one, alright, this one is x, is displacement. This one, negative, is showing that oppositely directed of the f and x. And k here represented by m omega squared. Because of, as you can see, the similar equation here. Alright, so that is why we call m omega squared is a constant here. So we can conclude that f here is proportional to negative x, of course, proportional to negative x. Alright, by using the Hooke's law equation. Alright, Hooke's law equation. Hooke's. Alright, so k is proportionality constant. Alright, okay, this one we already derived, I already show you. So from here, we can find a new equation for angular frequency or angular speed or omega. So from here, we arrange the equation. So we got a new equation for omega from this equation, k equal to m omega squared. So then we derive the equation of omega. So k divided by m square root of k divided by m. So we got a new equation for angular speed or angular frequency for simple harmonic motion. The unit is still same, radian per second. Alright, it's just a new equation which is related to the spring constant and the mass attached in the simple harmonic motion. Alright, this kinematic in a simple harmonic motion means that motion in a simple harmonic motion. Okay, alright, this is starting point until it's complete one cycle, which is a displacement versus time. Displacement x in meter and time t in second. So that is the kinematic in simple harmonic motion, motion in simple harmonic motion. Alright, okay, again, let's say you still not understand about the simple harmonic motion, you can refer to this animation. Okay, from here is negative, maximum negative amplitude, maximum in negative direction, and maximum in positive direction. This is a crest, this is a throw. Alright, crest is a puncak, throw is a, okay, yang bawah ni. Alright, rest and starting point. As you can see, what is the difference? Alright,